got to go through some more optimization. That's the name of the game. So this is, I want to do, I don't know if we'll get through much more than this one. This is a really important one though. This, you see this kind of problem all the time. So find the volume of the largest right circular cone that can be inscribed in a sphere of radius 13. What's it mean to be inscribed in a sphere? Say it again.
Never mind.
Yeah, that fits inside. Okay. So if you inflated a right circular cone inside a sphere, what's the biggest it could get? What would be the dimensions of that largest right circular cone that you could fit inside a hollow sphere of radius 13? Okay, so what do you think? Where do we start? We got a bunch of pictures that'll be useful. Okay, we know, well, you tell me. Where do we start? We're doing optimization, so what's the first thing we always try to do? Yeah, I got to get the objective function. The thing we're trying to maximize or minimize. What is it? Volume of a cone. And there it is. That's the volume of a right circular cone. Okay. What's the problem with the objective function? Two variables. So what do we need? Okay. Equation of constraint. Where's that probably going to come from? What's the constraint here?
Radius.
Yeah, the radius of the sphere. Good. So it's going to be inside that sphere, right? Okay, so how are we going to come up then? We have to be able to relate R and H somehow. So here's where the pictures are really important, right? We don't need a complicated 3D rendering here. We're just going to take a cross section through the middle. Everybody get that? Okay. So here's the cross section of the cone is just this triangle. The cross section of the sphere is the circle. The radius of the sphere we said was 13, so that's where the radius would show up in our picture. Agreed? Okay. Here's the height of the cone, and there's the radius of the cone. That picture, that's the crucial thing. That picture is what's going to allow you to come up with a secondary equation. So scrutinize that picture a little bit and see if you have any questions on that. See how we came up with that. Maybe it looks a little too complicated at first. At first, it probably just needs to look like this. There's the sphere. There's the cross section of the cone, right? There's the radius of the cone. And there's the height of the cone, right? Somehow we got to relate those to 13, so we need the radius in there. So if this is the center of the circle, then that's 13, that's 13. We wouldn't want that. That's 13, not that we need that particular radius, but those two are kind of useful. Everybody see where that's all this stuff's coming from now? Okay, yeah, we have a right triangle, right? And that's the kind of relationship we want. If we have a right triangle, then it's easy to relate the lengths of the sides. Okay, so So we're really, what's the right triangle that's going to be useful to us here?
Would it be 13 as that box R at the side?
Yeah, it's that little guy right there. See that one? That's the triangle that's going to be useful. So let's redraw that on a bigger scale. So we've got R. We've got, that's our horizontal leg, that's our vertical leg, and that's, whoops, that's 13. What's the dimension of that leg of the right triangle? Close. Oh yeah, you're right. H minus 13, yep, because there's 8, yep. H minus 13, everybody see that? The total height of the cone minus 13 gives us that leg of the right triangle, doesn't it? Okay. So what's that give us for our secondary equation then? So what is it? R squared plus equals 13 squared, yeah. Right? Okay, so there, I'm going to put a box around that. That's our substitution equation. Now, which variable should we substitute? Because we're trying to eliminate a variable from the volume equation, right? There's a really easy substitution there. Yeah, I mean, you want to solve for h in that secondary equation? Okay, but I don't want to solve, I don't want to even solve for r. What could I substitute for? Like, I could solve that for r. I mean, like if I solve that for r, then I'm going to have to square the r that I just solved for when I plug it in.
How are we supposed to solve for a variable that isn't there? I'm so confused.
What do you mean?
You said we need to solve for a variable, but there's only two variables.
You're right.
You said both of them. And
Yeah, you
said
did.
no.
You did. I agree. I wouldn't solve for either r or h.
Did you solve for B?
No. There's a much easier substitution.
You can put R in? No, you gotta come out. Oh, no, you know the radius.
Mm-hmm.
It's 13.
Could 169 be sub for the volume, or is that not work?
No, it's not the volume.
Oh.
Wouldn't the radius of the cone be 13?
No. No, because that's the radius. See, that radius is different than the radius of the sphere.
Oh.
What do I want to substitute there? You just want to look for something that I can solve for in the secondary equation and substitute directly into the objective function. It's, I mean, it's kind of r, but do you want
Oh,
r squared? You see what I'm getting at?
Oh, boy.
Do you see what I'm saying there? You don't really want to solve for r. You just want to solve for r squared because you don't need to substitute r. You need to substitute r squared. Were you guys all thinking that and you just... Okay, so yeah, here's what I wanted you to see. Look, that's the same as that. So just make that substitution. There's no reason to involve a square root in this and solve for r, right? We're just going to solve for r squared. What's r squared equal to?
69 minus 1h minus 7 squared.
Right. That's what we'll substitute. Okay, and then that's going to give us volume equals pi thirds times r squared, which is that stuff, times h. Everybody see that? Okay, and then I'd want to simplify that stuff in orange. So if I expand out h minus 13 squared, what's that going to give me? H squared minus 26h. Okay, and when I distribute that negative, it's going to just cancel that, isn't it? Right, so I'm really just going to get 26h minus h squared when I distribute that negative. Say it again. Yeah, I will. Yeah. So that's what I get from all the orange stuff. And then that's being multiplied by h and by pi thirds. And that's volume as a function of h. Everybody see that? Okay, and yeah, we definitely would want to distribute the white h because then we're just going to get a polynomial, right? It's easy to differentiate. Okay. So we get volume as a function of h equals pi thirds times 26h squared minus h cubed. And how about my domain? What would my domain be for this thing? What's the smallest that h could reasonably be?
0.
I mean, it could be, yeah, I guess it could be 0, but we could sort of disqualify some, like, here, I'll show you what I mean. Like if we, like if I pick a value of h that's really small, like let's say I pick a value of h that's like say this is my height. Right, then that's going to give me this cone. Agreed? Well, why would I pick that one if I could get the same radius and pick one down here that has the same radius, but a greater height? See what I'm saying? That would make no sense. For everybody get that? There's no way I would ever pick a cone that's completely in the northern hemisphere of that, you know what I mean, of that hollow globe. Everybody get, I mean, we could use those numbers in the domain, but there's no chance it's going to give us a maximum, right? So reasonably speaking, what would be the smallest value of h? Say it again. Yeah, it'd just be maybe 13, right? Like the smallest one we would consider would be a cone where the base of the cone was, you know, on the equator, right? That would be the smallest. What would be the biggest value of h? Height of this cone. 26, yeah. If I stretch this cone down and make it real tall and skinny, right, that's gonna mean that the height is gonna increase, the radius is gonna get a little bit smaller. The tallest cone I could make would be one that was 26, which would have no radius. That's not a very good choice, but that'd be my limit of the height. Does everybody see what I'm saying there? So I'm just gonna go from 13 down to 26. I could go from 0 to 26, but it's just, there's no point. I know that my solution would have to be somewhere on that interval, right? Everybody good? And there's no reason that, like, as the height increases, the radius is just going to change inversely, and, you know, one's going to get bigger, the other one's going to get smaller, okay? That makes sense? And from there, it's pretty simple, right? That's a really easy function to differentiate and find critical numbers for, isn't it? Right? So let's do that real quick though. Just kind of fun to finish these off. So what would my derivative be? We'll just leave that pi thirds out front. That's a constant. What do I get if I differentiate the terms inside?
4h minus
52h
yeah,
minus, okay? And we might as well take a second derivative real quick. What's that going to be? Okay, so we need critical numbers, right? What should I do to my derivative probably?
factor out.
Factor out, all I can factor out is an h, I guess, right? Yeah. So it's equal to pi thirds h times 52 minus 3h. So what are my zeros? V prime equals 0 at h equals what? 0, 52 thirds, and we're not going to keep 0. Right? 0, obviously, that's not going to, height of 0 doesn't do anything for us. So 52 thirds would be my one critical number I'd need to consider in my domain. At 52 thirds, is my second derivative positive or negative? Is it? Oh, it is. No, it's not. 6 times 52 thirds? Negative, right? Anybody get that? Okay, so then this is a pretty simple table. We could even just do it right up here. So we had 0 first derivative. At 52 thirds, horizontal tangent. Second derivative was negative, so what's that mean? Maximum, yep. We only have one critical number on our entire domain, so it is the maximum, so we found it, right? The height is just going to be 52 thirds, and we could find the radius by just plugging that in there and solving for r. Anybody see that? Okay, and we got it. Okay, we got our dimensions. What is 52 thirds? Okay, so then that kind of makes sense too. Just think about that. Just kind of picture what that's going to look like. It's going to be, the cone's going to be, obviously it's going to be a little bigger than 13. 13 would make sense. So it's going to be a little bit bigger. 4 bigger than 13, so it's going to dip down into the southern hemisphere by 4. That's going to be the biggest cone you could, most voluminous cone you could have anyway. Okay, give me 1 to 5 on that. Does that make sense? Okay. Okay, the other one that's really kind of a cool one to do, that's important, is one like this. So a hunter is at a point along a riverbank. He wants to get to his cabin, which is located 4 miles north and 10 miles west. Okay, the river runs east-west. Okay, he can travel 5 miles per hour along the river, but only 2 miles per hour on the rocky land. So how far upriver should he go in order to reach the cabin in minimum time? You see the dilemma here? Like if he were just to leave, that's where he is. There's the hunter and there's the cabin and there's the river. If he just strikes off across the ground, the problem is it's the shortest distance, but he travels pretty slowly on the ground. Right? So how are we going to set this up? There's our picture. I guess we need a variable. What's the only thing we can vary? So how far he goes along the river before he just makes a beeline for the cabin, right? That's the only thing you can control. So I could just call that x, I guess. Now here's another question though. Do I want to have, kind of think ahead a little bit here. Am I going to want to put the x there or as the base of that triangle, do you think? Probably the base of the triangle, because isn't it pretty likely that to find that distance I'm going to be using the hypotenuse? So I'm going to have to be doing some squaring and maybe some square rooting. So I'd rather make that a simpler looking variable, right? So if I call this distance x right here, that's the total distance along the river he would go until he's gone to a point that's perpendicular to the cabin. Then the point where he actually leaves the river would be called what? 10 minus x, right? Okay. So we got to come up with our objective function. What's the thing we're trying to minimize? Time. Okay, let's remind ourselves here, those of you who's in physics, so you guys have done lots of kinematic stuff. How do we relate speed or velocity to distance and time? Okay. Now we're trying to minimize time, right? So we'd want to solve that relationship for t. Yeah, so what would t equal? Yeah, distance over velocity, right? So the total time is just going to be the time along the river and then the time across the, what do we call that? The land, I guess. What do they call it up here? Rocky land, okay. We'll just call it T sub R and T sub L or something. Okay, what's going to be the time along the river? T sub R. So the distance, how far is he walking along the river? Along the river? He's going along the river, he goes 5 miles per hour, so that's going to be the speed or the velocity, right? But how far is he walking before he leaves the river? 10 minus x, right? Everybody see that? Yeah, so we're going to get a distance of 10 minus x over a speed of 5 miles per hour. And we're just going to assume that we're using miles and hours for our time and distance, right? Okay, what's going to be the time along the land? He's not walking x though, is he? How far is he actually walking? It's the hypotenuse, isn't it? Right? So we need to know, this is actually, I probably should do this. Let's see, let's go. So this is the distance he's covering. And what's that going to be? If that's x and that's 4 and it's the hypotenuse. But the square root of that, right? Okay. Everybody agree? Okay. So then come up with an expression for the time that he's spending crossing the rocky land. Divided by, how fast is he going? 2. Agreed? Okay, so what's his total time? Yeah, just going to be the sum of those two, the amount of time he spends walking along the river plus the amount of time he spends walking across the land is going to be the total time he's walking. Agreed? Okay. Well, what's nice about this? One variable, yeah. So it's already just t of x. Okay, what's our domain going to be? What's the smallest value that x could, and that's x, right? What's the smallest value it could reasonably have?
I'm sorry.
What's the furthest extent that the guy could reasonably walk along the river?
10 miles.
10 miles. That's not going to be it, but that would be if he walked all the way over 10 miles, so he's making the shortest possible distance across the land. But it's a pretty long total distance, right? So 0 to 10. Yeah, and then the smallest value of x would be if he took off immediately. So it's just going from 0 to 10. Everybody agree? And now we just flip into calculus mode and make a table. Okay? From this point on, it's just stuff you've been doing. This is a little tougher function because it's got a radical in it. Okay, let's do it though. What's t prime? I mean, that's really just 10 over 5 minus x over 5, isn't it? Everybody agree? The derivative I get from that first term is just negative 1/5. Right? Okay. How about the other one?
1/2 times. Okay, what's the 16? And then 1/2.
All divided by 2. That 2 and that 1/2 just cancel.
So it'd be x over 2 square root of x squared.
Yeah, good. So I get negative 1/5 plus, I've got an x on the top. On the bottom I have a 2, and that square root goes to the bottom. Agreed? That's my derivative. Do I want to take a second derivative? No, I don't, do I? I don't really want to differentiate that. It's a quotient rule with a radical in it. Nah, no point. What are we going to do instead? Yeah, we'll just do first derivative test. We'll get a critical number and just use the first derivative test to see if it's a minimum or maximum, right? We don't want to bother with a second derivative test. There's no reason to take the second derivative. Okay, so then t prime equals 0 when? When what's true?
When x over 2 square root of x squared.
Okay, good. Yeah, if I set this whole thing equal to 0, I would just add the 1/5 to the other side. Okay, so what would we do here maybe? Cross multiply. So that's giving me 2 times the square root of x squared plus 16 equals 5x. And then what do we do with a radical equation? Like that. Yeah, right? We're just going to, you isolate the radical and then take both sides to a power, right? Remember this stuff? We don't really want to, I mean, let's just square both sides. We don't want to make a fraction out of the right side. We'll just square both sides.
Multiply both sides by, or divide by 2.
Well, you could, but then I'm just going to get a fraction over here that I've got to square. Let's just square both sides completely. Okay, so then if we do that, if we square both sides, we're going to get the quantity 2 times the square root of x squared plus 16 squared equals the quantity 5x squared. What do I get on the left side? equals, okay, so then I just get what, 4x squared plus 64 equals 25x squared. So subtract the x squareds. Something like that. And then just solve for x. X squared equals 64, and that's not going to reduce, is it? No. X squared equals 64 over 21. So x would equal, obviously we're not going to take the negative solution, we'll just take the positive solution. So x equals the square root of 64, which is 8 over the square root of 21. What is that, roughly? Like 1.7-ish? Yeah. Okay, and then we would, remember, if we're solving a radical equation, we would have to plug that in and just verify that it works in the original square root equation. So if we had 8 over the square root of 21, would that work? We'd get, I don't want to put, it is going to work because there's no reason it wouldn't work. I'm not going to get a negative number on the other side of the radical. Everybody see that? If I plug that in. 8 over the square root. So I'd get 64 over 21 plus 16 times 2. Oh, that's going to be a mess. It would work. I promise you it would work. Right, when does it not work if you think back to when we did a bunch of these problems a couple years ago? It wouldn't work if somehow like I had a negative coefficient on that. If I was going to end up getting an output of a square root that was a negative number, which isn't going to happen, right? So it's a valid solution. So that's it. So what would he do? X is only 1.75, so he'd go pretty far down river, right? He's going to go, what, 8 1/4 miles down river and then strike off across that rocky ground. Because it's so slow, he goes pretty far along the river. What would have been the impact if he could have traveled like 4 miles per hour along the rocky land? What do you think that the calculus gods would have told us then? Yeah, right. I mean, he would have not gone so far along the river then, would he? Make sense? Okay. What if he could go the same speed on the river and the land? What do you think would have happened? What would he do? Just go straight. Yeah, he wouldn't go anywhere along the river then, right? And that's what the calculus would tell us. Okay. Give me 1 to 5 on that. Does that make sense? Okay. That's probably a good place to stop.